So next topic in matrices, very most important topic, eigenvalues and eigenvectors. As earlier we discussed, vector means in matrix nothing, that is a column matrix simply. So which type of column matrix we will call it as eigenvector we will discuss. A non-zero vector, a non-zero vector x is said to be eigenvector if there exists a scalar lambda such that ax equal to lambda x, then we call x is eigenvector of a corresponding to eigenvalue lambda. So like this we need to have one vector, a non-zero vector x. So eigenvector is always non-zero vector, very most important. Eigenvector never be a zero vector. So whenever if you calculate eigenvector, then you need to get a non-zero vector as eigenvector. So how to find this eigenvector and eigenvalues, with one example we will discuss. Before that example, so we are having ax equal to lambda x. If you take lambda x to LHS, ax minus lambda x equal to O. So take x common. Whenever if you take x common, you will have only lambda. But in matrix, we cannot subtract one scalar from one matrix. That's why you need to write here I. So this is one matrix. A minus lambda I is one matrix. X is another matrix equal to O. So this is just like Ax equal to O form. What is Ax equal to O? Ax equal to O is homogeneous system. So that means we need to solve this homogeneous system for non-zero solution. That non-zero solution is eigenvector. We need to solve a minus lambda I into x equal to O for non-zero solution. That we will get capital X. That capital X is eigenvector. For this, we are having a particular procedure to find eigenvector. First, procedure to calculate eigenvector. First, A be the given matrix. A be the given matrix. Next, write characteristic equation of A. Characteristic equation of A, which is called det A minus lambda I. This one is very easy. Simply we are going to subtract lambda from the diagonal and we are going to find det. For that, that will gives you one equation in lambda of third degree if A is 3 by 3. If A is 2 by 2, you will get an equation in lambda of second degree, that is characteristic equation. This characteristic equation plays key role to find eigenvalues and eigenvectors. So characteristic equation is very most important for calculating eigenvalues and eigenvectors. I will tell you one simple shortcut how to find characteristic equation while discussing problems. Now, you need to solve this characteristic equation. Solve characteristic equation. So characteristic equation is generally in lambda. If you solve characteristic equation, you will get lambda values. These lambda values are called eigenvalues. These lambda values are called eigenvalues. After finding eigenvalues, find out eigenvectors for each eigenvalue. If you get 3 eigenvalues, by taking one by one eigenvalue, you need to solve this homogeneous system. That means for each eigenvalue lambda, solve A minus lambda I into x equal to O for non-zero solution. That non-zero solution which is eigenvector. That non-zero solution only eigenvector. So like this, one can easily evaluate eigenvalues and eigenvectors of given matrix. First note down the given matrix, next write characteristic equation. This is characteristic equation. Solve the characteristic equation for lambda values. That lambda values only eigenvalues. That's why eigenvalues also called characteristic roots, because by solving characteristic equation we are getting. Next, by taking 1 lambda value, solve this homogeneous system for non-zero solution. That non-zero solution is eigenvector. So now we need to find eigenvalues corresponding to eigenvectors of one matrix, 3 by 3 matrix. For that, just now I said, first write characteristic equation. Characteristic equation of A. Characteristic equation of A. What is formula for characteristic equation of A? Det A minus lambda I equal to 0. Det 8 minus lambda minus 6, 2 minus 6, 7 minus lambda minus 4, 2 minus 4, 3 minus lambda equal to 0. Now actually you will evaluate this date by writing signs, cofactor signs, plus minus plus 8 minus lambda into, by deleting first row, first column, you will multiply these two minus these two, like that you are doing. But if you do that one, that is very lengthy process. Just now I said characteristic equation plays key role to evaluate eigenvalues and eigenvector. If characteristic equation is wrong, automatically eigenvalues will be wrong, corresponding eigenvector also you will get wrong. That's why I am giving one simple shortcut to find correct characteristic equation. That shortcut helps you to evaluate characteristic equation easily and very accurately. That is, minus lambda cube you will get for every characteristic equation of 3 by 3 matrix, and lambda square coefficient is sum of diagonal elements. Sum of diagonal elements into lambda square. Sum of diagonal. Diagonal means these three you need to add. Sum of diagonal. Next, minus sum of cofactors of principal diagonal. Sum of cofactors of principal diagonal into lambda plus det A equal to 0. So this is the simple shortcut formula to evaluate characteristic equation. I will explain each term how to evaluate, because characteristic equation plays key role to evaluate eigenvalues. So first minus lambda cube you will write as it is. Sum of diagonal elements. Add these three. 7 plus 3, 10. 10 plus 8, 18 lambda square. Sum of cofactors, I will evaluate separately. Sum of cofactors. Here many get confused. So sum of cofactors. To find sum of cofactors of principal diagonal only, these three. 8 cofactor will be delete 8 corresponding row, 8 corresponding column. 8 is in first row and first column. Remove first row and first column. The remaining elements, for remaining elements you need to find it. The remaining element is 7 minus 4 minus 4, 3. Now find out that one. 7 3s are 21 minus 16, 5. AD minus BC technique. Next for 7 7. So second row, second column is eliminated. Second row, second column if you eliminate, what you will get 8, 2, 2, 3. Second row, second column eliminated. 8 3s are 24, 2 2s are 4. 24 minus 4, 20. Next, for 3 3 corresponding column row. That is last row, last column is eliminated. Last row, last column is eliminated, remaining 8 minus 6, minus 6, 7. 8 7 are 56, minus 6 6 are 36. 56 minus 36, 20. This total sum gives you sum of cofactors of principal diagonal. That sum. 20 plus 20, 40. 40 plus 5, 45 lambda. Plus det A. Det A, you know very well by giving cofactor signs, plus, minus, plus. The det A also I am calculating here, ma. Det A. 8 into 8 cofactor already calculated. Here we are having 8 into 5. Minus into minus, plus 6. 6 corresponding column row is eliminated. Minus 18 plus 8. Minus 18 plus 8 is 10. Minus 10. Minus 18 plus 8. Next. Plus 2. Plus 2 corresponding column and row are eliminated. This 6 4 are 24. Minus 7 2s are 14. 24 minus 14, you will get 10. So 8 5s are 40. Plus into minus, minus 60. Plus 2 10s are 20. 40 plus 20, 60. 60 minus 60, 0. So det for this sum is 0. This is characteristic equation 1. Very easily you can calculate. If you want, you can calculate using regular method without using the shortcut also. That is little bit lengthy, little complex compared to this one. There is some chance of getting wrong coefficients. But here the coefficients were fixed. Sum of diagonal, simply add these 3. Sum of cofactors of principal diagonal, if you do like this, definitely you will get correct answer. Det A. This det A also you can calculate using calculator also. Now, here in these 3 terms, minus lambda I am taking as common. If you take minus lambda common, lambda square minus 18 lambda plus 45. So lambda will be 0. 15 3s are, if you solve this one, lambda square minus 18 lambda plus 45, 15 into 3. So the remaining 2 values what you will get? 3 comma 15. So finally eigenvalues are 0, 3, 15. Now we need to calculate eigenvectors corresponding to lambda equal to 0, lambda equal to 3, lambda equal to 15. Then we will get eigenvectors. 3 eigenvectors we are going to calculate now. So now I am going to find eigenvectors. Eigenvector corresponding to lambda equal to lambda 1 equal to 0. First one For that we need to solve one homogeneous system. A minus lambda 1 into y into x1 equal to 1. So now in A matrix from the diagonal you need to subtract 0. Subtract 0 means matrix won't change. 8 minus 0, 8. Remaining 2 same. 7 minus 0, 7. 3 minus 0, 3. So same A matrix you will get now. Minus 6, 7. Minus 4. 2 minus 4, 3. Here you will have x1, x2, x3 equal to 0, 0, 0. So this is homogeneous system. We discussed homogeneous system for non-zero solution. How to solve a homogeneous system for non-zero solution we discussed already. The procedure is write this matrix separately. Reduce that one to echelon form. Next to find rank. If rank is less than n, assume z equal to k. Next to find xy. That is very lengthy process. where it will take much time. Already problem is very lengthy. Again, if you apply that process, the problem is too lengthy. It is time taking. That's why what I am saying, very easy technique to find a non-zero vector x1, to get non-zero solution directly by solving any two rows in the given matrix. You can get now. So I am not going to apply row operations here. I am not going to find rank here. I am not going to compare number of unknowns with rank. Using one simple technique and easy technique, everyone can understand. From that we are going to find x1. That is, listen carefully ma. From any two rows of A matrix, write any two rows separately from second element to second element, like this. I am taking first row. What is second element ma? -6. Next element 2. Next element 8. Next element -6. Like this. Any two rows you need to note down like this. Second row, second element 7, -4, -6, 7. Very easy technique. Now write here x1, x2, x3. Now use AD minus BC. A into D, B into C. A into D, B into C. A into D, B into C. Like that. x1 by 6 4 are 24, minus into minus plus 24, 7 2 are 14. x2 by 2 6 are 12, minus 12 plus 8 4 are 32. x3 by 8 7 are 56. 6 6 are minus into minus plus minus 36. Here AD minus BC formula, you will have minus. Now x1 by 24 minus 14, 20. x2 by 32 minus 12, 20. x3 by 24 minus 14, 10, sorry ma, 10. 56 minus 36, 20. So now cancel with 10, 10 ones, 10 twos, again 10 twos. Now the first eigenvector you got ma, the first eigenvector is, I am writing here, first eigenvector is 1 2 2. Generally you need to calculate this one by assigning one variable k. That's why here you need to mention k. The first eigenvector for lambda 1 equal to 0 is 1 2 2. Like that you need to find eigenvectors for remaining two eigenvalues. So what is next eigenvalue ma? Eigenvector corresponding to lambda 2 equal to 3, 0 3 15 eigenvectors. Lambda 2 equal to 3. That means A minus lambda 2 into I into x2 equal to O. Subtract 3 from the diagonal, or in characteristic equation write in the place of lambda 3 also you will get. The easy technique is subtract 3 from diagonal from A. 8 minus 3, 8 minus 3, 5, minus 6, 2, minus 6, 7 minus 3, 4, minus 4, 2, minus 4, 3 minus 3, 0. Here x1, x2, x3, 0, 0, 0. Like this one, same procedure. How I evaluated first eigenvector, like that only. From second element to second element, from any two rows you need to note down. Minus 6, 2, 5, minus 6. 4, minus 4, minus 6, 4. This is x1, x2, x3. AD minus BC technique ma. AD minus BC technique. 6 4 jar 24, minus 4 2 jar 8. x2 by minus 12, minus again minus plus 20. x3 by 5 4 jar 20, minus 6 6 jar 36. 24 minus 8 ma, 24 minus 8, 16, x2 by 20 minus 12, 8, x3 by 20 minus 36, minus 16. Now cancel ma, with 8, x1 by 2, x2 by 1, x3 by minus 2. So the second eigenvector you will get, x2 will be 2, 1, minus 2. Next we need to find third eigenvector. Third eigenvector ma. So now last eigenvector ma. For lambda 3 equal to 15 we are going to find eigenvector. For that also similar procedure how we done previous two eigenvectors like that only. Subtract 15 from the diagonal. From the diagonal. 8 minus 15 minus 7 minus 6 2 minus 6 7 minus 15 minus 8 minus 4 2 minus 4 3 minus 15 minus 12. Now here x1 x2 x3 RHS 0 0 0. Again same procedure how we done like that only ma. Second element to second element. Minus 6 2 minus 7 minus 6 minus 8 minus 4 minus 6 minus 8 x1 x2 x3. Okay ma? x1 by 6 4 jar 24 plus 16, x2 by 2 6 jar minus 1 plus into minus minus 7 4 jar 28, x3 by 7 8 jar 56 minus 26. Now 24 plus 16 40 ma. x2 by minus 12 minus 28 also minus 40. Here you will get 20. Now cancel with 20 ma. If you cancel, what you will get? x1 by 2, x2 by 56, sorry, 7 8 are 56, 6 6 are 36 ma here. 7 8 are 56, 6 6 are 36, 56 minus 36, 20. So x1 by 2, x2 by minus 2, x3 by 1, 21 are 22 are 22 are. So the final eigenvector x3 will be k 2 minus 2 1. These are the three eigenvectors. This is the way to calculate eigenvalues and eigenvectors. Very most important topic ma. Here characteristic equation plays key role. That I said one small technique. If you can calculate characteristic equation correctly, automatically you will get eigenvalues correct. Eigenvectors also you will get correct. So concentrate on that shortcut ma. But these shortcuts sometimes fails. When this shortcut fails, whenever if you write from second element to second element, if you calculate this one, here if you get 3 zeros, then this shortcut cannot be applied. Then what to do? Then change the rows. If you take first 2 rows, if you get 3 zeros, then change the rows. That means first row or third row, or second row or third row, till you get at least one non-zero. You may get 2 zeros, at least one non-zero value you have to get now. If you get 3 zeros, this technique fails. Remember this. Whenever if you get 3 zeros, change the row. That is the technique. Next problem, same on eigenvalues and eigenvector, but this is a little bit different. That's why we are discussing. In the previous case, we discussed distinct eigenvalues. Now we are going to discuss for repeated eigenvalues how to find eigenvectors. For that, as usual, write characteristic equation ma. Characteristic equation of A, which is det A minus lambda I equal to 0. Det 3 minus lambda 2 2 1 2 minus lambda 2, minus 1, 0 minus lambda is minus lambda equal to 0. Now, by using the technique which I said for the previous problem, the technique again I am writing very clearly, minus lambda cube plus sum of diagonal elements into lambda square minus sum of cofactors of principal diagonal into lambda plus det A equal to 0. Using this simple shortcut, I am going to find characteristic equation now. Minus lambda cube, sum of diagonal means you need to add these three. If you add the three elements, 3 plus 2 plus 0, 3 plus 2 5 lambda square minus sum of cofactors of principal diagonal. In the previous problem I said how to calculate sum of cofactors of principal diagonal. Sum of cofactors means for principal diagonal elements are 3, 2, 0. For 3, 2, 0 we need to calculate the cofactors. 3 cofactor, 3 corresponding column, row is eliminated. What is remaining elements you are having? 2, 2, minus 1, 0. Now use AD minus BC technique. 2 into 0, 0, minus into minus plus, 2 1s are 2. So that means 2 you will get, 0 plus 2, 2. Next for 2 corresponding column, row is eliminated. The remaining elements what you are having? 3, 2, minus 1, 0. Second row, second column is eliminated. Now 3 into 0, 0, 3 into 0, 0, minus into minus plus, 2 only will get. For the last element 0. 0 corresponding column, row is eliminated. Last row and last column. What are the remaining elements you are having? 3, 2, 1, 2. 3 2s are 6. 6 minus 2, 4. Now add all these three more. If you add all these three, what you will get? 8. 8 will be the sum of cofactors of principal diagonal. Next we need to find det A. Det A I said how to calculate det A by writing cofactor signs plus, minus, plus. Now I am going to calculate det A. So for 3 already we calculated cofactor. So take that one 2. 3 into 2 minus 2 into 2 corresponding column, row is eliminated 1 into 0, 0 plus 2. 0 plus 2, 2 plus 2 into 2 corresponding column, row is eliminated. Now 1 into minus 1 plus 2 minus 1 plus 2 1. Now simplify 3 2s are 6 minus 4 plus 2. 6 minus 4 plus 2. 6 plus 2 8. 8 minus 4 4. So what you will get? Det A is 4. So this is the characteristic equation. To solve this characteristic equation, generally there are so many methods, but this is a third degree equation. We need to use synthetic division, which you may learn in lower classes. Synthetic division means first write all coefficients. First lambda cube coefficient minus 1, lambda square coefficient 5, lambda coefficient minus 8, constant 4. Now using trial and error method, just try with lambda equal to 1. And one more technique to decide lambda equal to 1 is factor or not, simply add all these coefficients. If you add all these coefficients, if you get 0, lambda equal to 1 is definitely root. For that, 5 plus, first add plus terms, 5 plus 4, 9. Negative terms, minus 8, minus 1, minus 9. 9 minus 9, 0. That means lambda equal to 1 is definitely a root. Definitely root means finally here you have to get 0. So I am explaining synthetic division to find roots. First write coefficients. Next try with 1 by writing 0. Add these two. minus 1 plus 0, minus 1. Multiply this minus 1 with this. Minus 1 into minus 1, minus 1. 5 minus 1, 4. 4 into 1, 4. Minus 8 plus 4, minus 8 plus 4, minus 4. Minus 4 into 1, minus 4. Definitely you will get 0 here. 4 minus 4. So now lambda minus 1 is 1 factor. And remaining is, these are coefficients of second degree equation. Already 1 degree is cancelled. Minus lambda square plus 4 lambda minus 4 equal to 0. Clearly here we are getting 4 is 2 2s are 2 2s are 4. That means this can be written like lambda minus 1 into lambda minus 2 whole square. If you want, you can take minus common. A square minus 2ab plus b square form you will get. Then lambda values are 1, 2, 2. These are eigenvalues. Eigenvalues of this matrix are 1, 2, 2. This is the special case which I said. In the previous case we got 3 distinct eigenvectors, eigenvalues, but now we got one repeated eigenvalue. Now the question is how to find eigenvector for repeated eigenvalue. That we will discuss while discussing eigenvectors now itself. Next, we are going to find eigenvectors for the eigenvalues. Eigenvector corresponding to eigenvalue lambda equal to 1. For that we need to solve homogeneous system. A minus lambda 1 into I into x1 equal to 0. That means subtract 1 from the principal diagonal. 3 minus 1, 2, 2, 2, 1, 2 minus 1, 1, 2, minus 1, minus 1, 0 minus 1, minus 1. x1, x2, x3 equal to 0, 0, 0. Subtract 1 from the diagonal. You need to subtract 1 from the diagonal. 3 minus 1, 2, 2 minus 1, 1, 0 minus 1, minus 1. Now as usual write from second element to second element. 2, 2, 2, 2 only. You are having 3 2s. 2, 2, 2, 2. Complete 4. 1, 2, 1, 1. Now x1, x2, x3. x1 by 4 minus 2. x2 by 2 1 are 2 minus 4. x3 by 2 minus 2 1 are 2, 2 1 are 2. Like this you may get 1 0 you may get, 2 zeros you may get. x1 by 4 minus 2 2. x2 by 2 minus 4 minus 2. x3 by 0. Now cancel with 2 you will get first eigenvector. 2 1 are 2 1 are 0. 1 minus 1 0. This is the first eigenvector. Coming to the second one, eigenvector corresponding to lambda 2 equal to 2. Lambda 2 equal to 2. Same heading. Here I written 1, here 2. Heading is same. Now we need to solve this homogeneous system for non-zero solution. For non-zero solution, I am taking here x. I will tell you why I am taking x. So subtract 2 from the diagonal. 3 minus 2. 1, 2, 2. 1, 2 minus 2. 0, 2. Minus 1, minus 1. 0 minus 2. Minus 2. x1, x2, x3. 0, 0, 0. Now we need to find eigenvector for repeated eigenvalue. This is repeated. Previous one is distinct one. For distinct eigenvalue, usual procedure writing from second element to second element. But for repeated eigenvalue, for one eigenvalue we are going to find two eigenvectors at a time. For that, no need to apply this technique. For repeated eigenvalue, there is standard technique by assigning two variables k1, k2 like this. Let x3 equal to k1, x2 equal to k2. By assuming like this, find out x1 in terms of k1 and k2. So what you will get? First equation I am writing x1 plus 2x2 plus 2x3 0. Right in the place of x3 k1, x2 k2. x1 plus 2k2 plus 2k1 0. So x1 equal to minus 2k2 minus 2k1. So finally eigenvector x will be x1 is minus 2k2 minus 2k1, x2 is k2, x3 is k1. Now separate k2 terms. K2 terms. First write only k2s like this. First k1, next k2. First k1 minus 2k1. Do you have k1 in the second term? No. 0. K1 plus k2 terms minus 2k2. Here you are having k2. Do you have k2 in the last? No. 0. Now, if you take k1, k2 common, you will get two eigenvectors. That will be the remaining two eigenvectors. What I am saying, if you take k1 common, k1 common minus 2, 0, 1. If you take k2 common minus 2, 1, 0. These two are the remaining two eigenvectors. First eigenvector 1 minus 1, 0. Minus 2, 0, 1, minus 2, 1, 0. You can use this technique for all repeated eigenvalues. When eigenvalue repeats, simply assume like this, find out two eigenvectors. For repeated eigenvalue. For distinct, this procedure. For distinct eigenvalue, same procedure. Like this you need to follow. For previous problem I said, the same technique for distinct. For repeated, this is standard procedure. Okay, ma, clear?